Here we are in Elementary Calculus, Chapter 4, Section 5, where we're going to talk about derivatives of logarithmic functions. And in this section, the first thing we need to talk about is taking the derivative of the natural log of x. Here we see that the derivative is equal to 1 over x. Doesn't look like we're applying the chain rule there, although invisibly we are, and I'll talk with you about that in a moment. And the second highlight here is, remember that the natural log is actually a logarithm that has a base of e. And so here, in this second box, we're seeing all the rest of the logarithms. So generally speaking, a log with base a. And that is equal to not just 1 over x, but in the denominator you're seeing a multiple of the natural log of a. If we applied that idea to the natural log derivative that we saw at the top of the screen, if we were to introduce into the denominator that same multiple of the natural log of the base, you would have a multiple of the natural log of e in the denominator. However, the natural log of e is equal to 1. So in that first sort of definition or illustration, there is an invisible multiple of the natural log of e in that denominator. But you won't ever have to worry about it. Just remember that the derivative of a natural log of x is equal to 1 over x, and if it's got a base of a on your log, then you need to include a multiple of the natural log of a in the denominator. And then we're seeing real implementation of the chain rule here, where as we take the derivative of the natural log of an expression that's very simple like x, we've already seen the result of that derivative. But if we move to the right and we're taking the derivative of a log base a where there's a function or an expression in here, then what happens is we do implement the chain rule. And this is a fine way to write it. If it were me, I think maybe I would do it a little bit differently. I think I would have included this multiple of g of x and this multiple of the natural log of a in their own denominator, because it follows the format of what we've seen already. So that's the natural log of a times g of x. And then the chain rule tells us that we have to multiply by the derivative of this inner function. And I would include that kind of after the fact, whether it's next to the fraction or sort of up in the numerator. But you can see how this first part of the process looks very similar to when we were taking the derivative of the natural log of just x. However, is going to make it easier for you to remember what to do when the time comes. I'll leave it up to you. Similarly, when we go into the second row of statements here, which involve the natural log, again, in this denominator over here, we're not seeing a multiple of the natural log of e because that's equal to 1. And in this denominator over here, we're also not seeing the multiple of the natural log of e because it's equal to 1, which makes this fraction very compact and tidy. It is, though, realize it's the same as this. Okay, these two are equivalent, except that if we get rid of that multiple of the natural log of e, then you only have one factor in the numerator and one factor in the denominator, and those factors are here. G prime on top, g on the bottom. Okay, so let's see about implementing some of these new tools. Example number 1 asks us to find the derivative of this function. And I know, at least the way that I think of it, is that the derivative with respect to x of the natural log of some function g of x is equal to 1 over g of x And then the chain rule says I have to multiply by the derivative of g of x. You could write this as one fraction where g prime is in the numerator over g of x, or I've written it as this product, because in my mind the pattern is that when I'm implementing the chain rule, that there's this extra multiple that happens on the end. So that's again why I've written it this way. Okay, so now we can just fill in these blanks. I've got 1 over 8x. My g's and 8's look a little too similar. Let's make that look more like an 8. There we go, 1 over 8x. And then the derivative of 8x is just 8. Those 8's are going to cancel out, and we're left with 1 over x again. It's curious. Yeah, for sure. Let's double check. Did we really do that the right way? Yeah, it's a natural log function, right? So I'm looking here, taking the derivative of a natural log function, and inside of the natural log is another function, 8x, okay? And the denominator has a g of x in it. Yep, that looks pretty good. And in the numerator is g prime, and the derivative of 8x is indeed just 8. And then when you simplify, those 8's are going to cancel, and we're left with just 1 over x. If that function 8x inside of our natural logarithm were more complicated, in fact, let's just do another example. What if we had our original function was y equals the natural log of, how about 8x squared plus 5x plus 2? Why not? Then our derivative with respect to x would equal 1 over the entire original function, 8x squared plus 5x plus 2, times the derivative of that function, which is 16x plus 5. Nothing's going to cancel here. That 16x plus 5 slides over into the numerator position. And that would be your derivative. If you could reduce it, maybe if they were all even numbers or something, and you could reduce by a factor of 2 perhaps, maybe there were, now you wouldn't even end up with x's left in all of those. So yeah, unless there were some really cool factoring that could be done here, this is where it would end. So that first problem that I wrote in blue, kind of a coincidence that it turns out to equal that the derivative is 1 over x, but just realize that it's not always going to clean up quite that nicely. Here we want to take the derivative of a function that contains a logarithm and an exponential. So we've got e to the x is the exponential, and the natural log of x is the logarithm. And these two things are connected by multiplication. So we're going to be using the product rule. The e to the x is a factor, the natural log of x is a factor. So let's use the product rule. dy over dx, the derivative of y with respect to x, is equal to. The order in which you do these doesn't matter. There's probably an industry standard, but since it doesn't matter, I never commit it to memory. Whether you take the derivative of the first factor first, or the derivative of the second factor first, it doesn't matter, because we're going to have a plus sign in the middle, and if we had to switch them around the plus sign, that's okay. So I'm going to take let's write this one all the way out. I'm going to take the derivative of the e to the x, and then multiply it by the existing factor of the natural log of x, plus we'll leave the e to the x alone this time, and we'll multiply by the derivative with respect to x of the natural log of x. So this is the product rule. Derivative of the first times the second plus the first times the derivative of the second. And then let's take our derivatives. Derivative of e to the x is boring. It's e to the x times the natural log of x plus e to the x is still there, and the derivative of the natural log of x is 1 over x. So this way you can see all of the pieces of this puzzle kind of playing out one at a time. And then all we have to do is clean up a little bit. The first factor, I would probably still write it just this way, e to the x ln x plus, and then this one I would turn into a fraction, e to the x over x. And that is your first derivative using the product rule and derivatives of exponential expressions and the derivative of a logarithmic expression. These are going to get more complicated. Instead of e to the x, it could be e to the square root of x to the 5th power minus blah, blah, blah. You could put trigonometric functions in here. And it could be the natural log of the sine function. Natural log of the sine of x squared plus 4x plus 2, right? You can take these and go to the moon with them. But always refer back to your basic properties as these get more tricky, and you have to be mixing your properties or processes. Here we've got the product rule and exponential and logarithmic. You might have to do product rule and exponential and chain rule. Chain rule is usually the one that sneaks in over and over again, making our problems a little more tricky. More tricky like this one instead of just this very simple 1 over x. What else? Oh good, we have an application problem. So here, let's zoom out a little, got it all, okay. Suppose that the demand function for x units of a certain item is, and there's your equation, P is the price per unit in dollars. So our price is being driven by demand in this particular model, and we want the marginal revenue function. How is revenue created? I don't even see a revenue equation here. Revenue is generated by taking the number of units that you sell and multiplying it by the price per unit. All right, and hey, we have a price equation. I would say that this is revenue as a function of x, where x is the number of units. Okay, so that makes sense. The amount of money coming into the cash register is driven by the number of units that I'm selling, and that total revenue is determined by taking the number of units that I'm selling and multiplying by the price per unit. Okay, so now let's replace P with our demand function. So we have x times 100 plus 180 natural log of x plus 5, and that's all being divided by x. So this is our revenue function, and we want to find the marginal revenue function. And as you'll recall, we've mentioned this a few times, that marginal is a key word that's telling us to take the first derivative. It's the rate of change of, in this case, revenue. So we have to take the derivative of this expression or this function, and there's multiplication happening right here. So should we use the product rule? We could, I wouldn't. If I were you, the first thing I would do is distribute, and it's going to make finding our first derivative a lot easier. So let's distribute. I've got 100x plus, now this x, once it multiplies, right, so we're distributing it, x times the 100 is the 100x. When the x multiplies into that second term, it's going to cancel with the x in that denominator, and so I have just 180 natural log x plus 5. So again, this x is this x, but it canceled with this x. Little tricky. Now what? There's no more distributing that we could do, so I think it's probably time for us to find our marginal revenue function. So let's calculate r prime of x, the first derivative. The first derivative of our first term, 100x, is equal to 100. Taking that exponent of 1 that's here, multiplying it by the 100, then decreasing that exponent, which makes it a 0. X to the 0 is equal to 1, so you have 100 times 1, which is 100. There's our plus sign, and here's 180, and we're going to multiply by the derivative of this natural log function. Remember that the derivative of natural log is equal to 1 over our function, x plus 5, times the derivative of that inner function. It's the chain rule. We have to multiply by the derivative of x plus 5. It so happens that that's equal to 1. The derivative of x is equal to 1. The derivative of 5 is equal to 0. 1 plus 0 is 1. And so we have this multiple of 1 out here. If you want in your notes to include that 1 came from taking the derivative with respect to x of our inner function, x plus 5, that's not a bad idea. If you've got the handle, a good handle on the chain rule already, maybe you don't need to include that note. And so we'll just clean this up a little bit. I will happily say that that is my marginal revenue function. Interpret this result. Well, we didn't, I'd love a result of like plugging in an x value, but remember that the marginal revenue function describes the rate of change in revenue at some particular x value. Now that x value represents a number of units. So let's say we plugged in, let's plug in 175 just for funsies. Let's find r, that's an f. Let's find r prime of 175. That would equal 100 plus 180 over 175 plus 5, and that's going to equal 100 plus 1, which is 101. What does that tell us? It tells us that when we're producing 175 units, there's a certain amount of revenue, and that if we increased to 176 units, that our revenue would increase by $101, presumably. We weren't given, it's just price per unit in dollars, not in millions of dollars or anything like that. So again, the marginal revenue at the point where you're producing 175 units is equal to $101. And what that means is that your revenue would increase, because 101 is positive, your revenue would increase by $101 if you were to move forward and produce 176 units. I talked about this at the end of the previous section video, and so you might want to jump back and just check out the last couple of minutes of that video, because I'll remind you again here that the first derivative is talking about rate of change, like slope, like rise over run, like change in y over change in x, or in this case, it's change in revenue over change in units produced. And so this 101 actually means 101 over 1. Surely those are equivalent. Let's put units on there. It's $101 over 1 unit. And if you think of it as rise over run, if you increase your number of units by 1, as in moving horizontally 1 unit on a graph, then your rise in the y direction would go up $101. So an increase of 1 unit causes an increase of, this is so strange, causes an increase in the y direction of $101. And that's slope, rise of 101 over a run of 1. Strange, but that is indeed what this describes. Okay, my guess is that that was our last example for this section. It was. Hopefully these couple of illustrations help to get you started. But remember, this is not the end-all be-all. There are more difficult problems out there. So keep mixing these ideas of your derivatives, Remember what derivatives are describing: rate of change, marginal, revenue, cost, profit. Marginal means derivative, means rate of change as you're moving from one unit to the next, perhaps. And you're going to have to combine these derivative processes, the product rule, the quotient rule, the chain rule, and then these other sort of anomalous things where we have natural logs and exponential functions. Got to keep mixing all that together. Keep looking at the solution processes for a variety of examples that are increasing in the level of difficulty. Those processes are going to get longer. Just make sure to keep going through one line at a time and looking for what's changed as that solution process has gone along. Why have those different changes been made? Was there a natural log? Was there an exponent? Was there a product? Did I need to use the chain rule? It's going to require some patience, but you can do it. Just keep an eye out for what's happening as you go along through those processes. All right, thank you so much. I think this is actually the last section of Chapter 4, which means I will see you again in Chapter 5. Thanks so much.